Okay, so my name is Hacohen, and I'm from Deep University, and thank you very much for the introduction. Basically, if you guys have any questions, then feel free to ask. Much rather have a conversation than a one-side talk. So just stop me anywhere and ask. There's no I just can do less slides. It doesn't matter to me. So so just carry on that. And today I'm just going to present the works I did in my PhD. So pretty much when I started my PhD, the question I wanted to ask is how deep models learn, how neural networks learn in general. But this appears to be a very big question, so I couldn't really answer that. So I boiled down to an easier question, which is what the difference is between humans and machine when it comes to learning. But apparently this is also a very big question. And so instead, what I'm going to do is I'm going to show you works that I did in during my PhD that draw connections between human and machine learning. And we're going to see how human learn in some motivation from human learning, and we're going to see how we can draw connection from that back to neural networks, and maybe understand something about how neural network works and how can we make it even more closely related to human. So I'm going to focus in this work about curriculum learning and active learning, and then talk about the learning order of neural networks themselves. So I'm going to start with the curriculum learning. And to start with that, I'm going to start with an example of some analogy between humans and networks. So when we teach humans, many times what we do is we simply have a student, which is some human, and a teacher, which is some other human. And the teacher wants to teach some task to that student. And if I try to do that analogy to neural networks, I can think of the student as the network itself, which I want to learn something. The data that I'm training or the task that I'm doing would be the data that I'm trying to learn the model. And the teacher could be any one of the learning algorithms we use to train that network. So usually it's some variation of stochastic gradient descent, but it could be anything you do. And when we teach humans, then what we usually do, we don't just throw at them examples, but let's suppose we're going to teach humans how to do, I don't know, the differential equations or stuff like that, okay? Then I'm not going to say to the human, here is differential equation, please solve it. I'm going to break it down into steps. I'm going to start and teach him how to do addition, and then maybe how to multiply two numbers, and then maybe how equation works, and I'm going to break it down to many steps. And these steps I'm going, and at the end I'm going to teach him, okay, so this is how differential equation works. How we do it when it comes to neural networks. So in neural networks, you just take 300,000 differential equations, give them all to the model, and say, if you can please memorize these, you probably know how to solve differential equations. And this doesn't really make sense to us, because this is not really how humans do it. And we wanted to try and build curriculum also for the networks. So maybe to take the problem and somehow deconstruct it into put some structure in it, and maybe that could be helpful for the network too. And so that's like the motivation of that work, and something not working here now. Sorry. Okay. So what we want to do, we want to take our data and somehow deconstruct it into and other tasks, and then try to show the networks the network data from easy to hard in some sense. But we are focusing on vision. So asking which image is easier or harder to classify is not very clear, right? If you have these two images, you can't really tell me which one of them is an easier dog to classify. It could be any one of them. in some sense, in some cases, in the very extreme cases, it may be easy to do that. If the two images look like that, then you can tell me, okay, the left image is much easier than the right image for some sense. But in general, we cannot assume that we know that. And even if we could assume that we know that, we cannot assume that humans and networks are the same in that sense of what hardness is. Maybe the left image is much easier for humans, but maybe it's not that much easier for networks. Maybe it is, probably is, but we don't really know. So the main question we need to ask is what kind of examples are harder than the other. However, this is not going to be enough for us. Even if we do know how harder, even if we have a function that decides which example is harder than the other, we also need to decide on the pace. If I again try to give the analogy to humans, then if I'm trying to explain something to humans and I do it too slowly, they might get bored and fall asleep. But if I do it too fast, they might just lose me and be overwhelmed and don't know what I'm talking about. So I also need to decide the pace in which I introduce new stuff to the network while I learn stuff. Okay, so this is how we deconstruct the problem. And now let's talk about what we actually did. So to build the curriculum learning, but the algorithm is very, very simple. First of all, we need a function that decides which image is harder than the other. Then we need the function to decide the pace, how much we should, how many examples we should show at each point. And then we just take the data, we sort it according to hardness, and then we show at the beginning easier examples, and then asking our pacing function how many examples we should add at each time, and then just add gradually harder and harder examples. Okay, so this is all theoretical, but how do I decide? Do I decide which examples are? I think that's coming from someone in the Zoom. So
hello, David.
Yeah.
Well, you will see.
Yeah. Okay. So that was yeah. Okay, a detour to David. Okay. So again, we can't really know. This is vision dataset, so we can't really know which example is easier or harder, and we don't know even if humans know how to do that for networks. So the first thing we did, just to show that it's even possible to arrange the data in a meaningful way, we decided to let networks decide the hardness between images. So what we did, we wanted to train our dataset on some small training set. So what we did, we took a larger data set. Let's say we wanted to train on CFAR, so we took ImageNet, which is larger, and trained some model on that, and then simply did transfer learning into a very small model. So now we have a model that knows a lot of trained on a lot of data. Trained on a lot of data, and we somehow distilled its knowledge into a smaller model. And then we ask this model to sort the training data according to its loss. So if it's basically add our time on an example, we claim this example would be very hard, but if it managed to classify it very easily, then we said this example is easy. So now we have a specific ordering of all the data.
This model that you've trained on ImageNet is now being fine-tuned on the new task.
Yeah.
To train a new network is being trained from scratch for a new task.
Yeah. So I have this network that is very good on this task, but and I ask it, okay, now that I trained it on this task, which example will out for it and which not. Okay. So now I have an ordering of an example from easy to hard. And I use this, and I order this data from scratch. And then I train my network student on exactly the same data, but using the algorithm I just showed. So at the beginning, I show it only easy examples, and then gradually harder and harder. Yeah. So No, in the second row, the train set is C5 or something. It's a data, a different data from ImageNet, but it's smaller than ImageNet.
How does the teacher know the new train set? Just when
So by transfer learning, I just I took the new training data and then fine-tuned the larger model for that data. Okay, so I now have my training data ordered, and they can train the exact same network.
Sorry, maybe you'll answer this later. Why does it matter that it's initially trained on the validator? Like, do you have
Okay, so
why can you not just train the student the first time without curriculum learning?
so
And then
yeah, that's I'll get to that.
Okay.
That's a good idea. It works, but but the reason basically this should have been more like a proof of concept type thing, because before this work we didn't even know that that changing the data in any way should even work a little bit. So we wanted to see if there is any order that could help, so we can use like bigger tools. We can say, and having larger data give us more power. So this maybe it's a way to incorporate more knowledge into the data. Okay, so I'll skip that one and just show you the results. But basically, the black line here is just training the network without any curriculum, just by taking random examples. And the blue line is by showing it examples using the curriculum learning, showing the exact same data set. We didn't change not data set and not the network, but we just showed easy examples and then examples of going faster and faster and faster. The red line is doing the exact opposite of the curriculum. It's showing hard examples at the beginning and then showing easier and easier examples as we go along. Just taking the scoring function and reverse it. And the random one is using the same idea of showing a little bit of examples at the beginning and then more and more gradually, but the examples we show at the beginning chosen as random. So we can see that the random is even worse than just doing a vanilla. So doing this whole concept of showing little amount of example and then increasing, it's not a bad idea. It's not a good idea in general, but if you introduce the curriculum to that, then it's actually surpass both the vanilla and the random, and you get learning that it's much faster and gets to a better minimum. Yeah.
Is this revealing little by little out? Is it that you're revealing a little bit and then also creating updates on the reveal, or is it revealing a little bit in one update and then revealing something else?
Okay, so this is the one thing that I skipped. So basically, what we did is here on the x-axis, y-axis, I show how much of the data I reveal at each point, and on the x-axis, it's the time. So at the first 500 iteration, we only reveal. So what we did is actually that red line over there. So at the first 500 iteration, we revealed about 10% of the data, and then about it's even less, like 2%, 4%, 8%, 16%. So we reveal a small fraction of the data, and then every few iterations we double it. We just at the beginning we reveal 2%, and then 4%, and then 8%, and stuff like that. Did that answer your question?
I think partially. I guess I'm curious if you're iterating over the same examples more than once.
So yeah, the iteration here. So one epoch of the data would be something around like 30 iterations or something like that. So and because there are only 10% of the data or less, then even I iterate more and more and more on every example as I'm earlier on. So on the easier examples, I iterate much more than on the others. But at the end, I iterate over all the examples.
So it's not that you're only showing the hardest examples. You're not constructing your mini batches from only the hardest examples. You're constructing it on the entire range.
Yeah.
From the easiest to the hardest.
Yeah, at the beginning it's only easy, and then it gets easy and medium, and easy and medium, and a bit hard, and then everything. And the reason we do that is because if we focus on only the hard one at the end, then the distribution is going to be different, and we're going to get possible forgetting, and then the entire thing stops working. Okay, so this is the results for one data set, but we did it on several others and didn't want to show all the graphs, but they all look pretty much like that, and that's just the final answer. Okay, so back to the idea that you suggested. Why do we do it with a larger teacher, with larger data? So doing it with a larger teacher allows us, it's much more robust, and we get better performance than doing it with anything else. However, it's only a proof of concept type of thing, and it's not very scalable to other networks, because if you want to train something on ImageNet, you need to find data sets that are larger on ImageNet. So what you can actually do in practice is what we call a curriculum by self-tutoring, which is just take your network, train it once on the data. Now you have a model that knows what is easy and what is hard on the data. Take this model, order the data according to this model, and now run curriculum learning. This also works much less than the other one. I mean, it's more sensitive to hyperparameters. Yeah.
So my question is, just now you show the graph and also you have improvement in the accuracy and also you learn fast, but that's as a side of the first big network training on a very big.
Yeah, that's true. This is a proof of concept that even ordering the data affects somehow. It's only proof of concept. It's not practical. But now I tell you, I can make it practical by doing a much simpler thing, which is just taking the model, training network on it, and then run this network to order my data and then train it again. So it's just 2 times training. It's not that hard to do.
Also, kind of like the opposite of boosting.
Yeah.
Something like that.
Yeah, so we actually have a few works on that. That's just one of them, and the other focused on the theory, and then we compare it to boosting, and then we show. But it's a bit out of scope for this stuff. But yeah. Sure. Okay, so the advantages of the self-tutoring is that it's scalable. It's much faster. You can run it on anything. But the improvements are not as are smaller. I mean, this blue line will go down a bit more, and it would be more sensitive to hyperparameters. So this would work. This would work on many ranges of hyperparameters, but you need to play with hyperparameters more to get it to work with self-tutoring.
So these are results with those.
This is results for transfer. Yeah. Okay. So let's do a quick summary of this. So basically, what I wanted to say about that is that some insights from human work on networks. Okay, so we started with the insight that curriculum works well on humans, and now we managed to transfer at least part of it to networks. We have much more results about curriculum learning than that, and you can either see them on my page. And Daphna also worked on curriculum before I even came, so she has many more papers about that if that's interesting to you. But what we did here is only a very specific type of learning, right? Only learning that happens in class with a teacher and students, and it's supervised. And this is not what most of human learning looks like. Most human learning looks like you have only few examples, if any, and you do it more unsupervised way and stuff like that. So now we want to take this sort of idea and try to do it in an environment where you have much less examples. Let me see that I'm not running over. Okay, so I'm on time. And so what we should do when there is much fewer examples, and basically what I'm going to claim here that you should do pretty much the same idea. You should present easier examples at the beginning and other examples at the end. And now we're going to look on that from the perspective of active learning. So first of all, let me give you the motivation from humans again. So let's suppose you can only show your child one image of a dog, okay? And you need to use that image to explain to him what a dog is. Would you prefer to show him the image on the left or the image on the right? So I would argue that you want the image on the left. You may not agree with me, but my intuition here is that assuming we do want the image on the left for children, why wouldn't we want the same image for networks? And for this, I'm going to introduce you a bit to active learning. I guess most of you know what active learning looks like, but let me introduce it anyway. So in active learning, we have a large pool of unlabeled data, and we have a small model. That doesn't necessarily have to be small, but we have a model. And this model requires examples, and we need to decide which examples to label from that unlabeled pool that would most benefit this model. And we get a specific budget. So they tell us we can only label, I don't know, 200 examples, and we need to choose the examples that would most benefit the model. And the question is how to do that, which example would be better. And what most methods do, so most of the previous work, they assume you have a very large budget. They assume you can label many examples. And if you can label many examples, what they suggest you do is something that's called uncertainty sampling. So you take your data, you have, let's say, 10% of the data is already labeled. You train a network on these 10% of the data, you get a model. You take this model and you ask which examples are this model is most uncertain about. And this is the examples they suggest you should annotate. And these tend to be the very atypical examples because the model already seen 10% of the data, so we already pretty much know how a dog looks like. So he's certain about the dogs, but uncertain about the dog that looks like Pusha. And we say that when you have a very low budget, when you can only do a very small amount of labeling, then you should do the entire opposite of that. So instead of taking the examples that are the most uncertain, you should take the examples that are most typical. So this is how we differ from different works. And I want to give you an example of how. So we tackle this from a theoretical point of view, but I'm going, instead of diving into the theoretical part, I'm just going to give you the examples that show how we do that. So let's suppose you have this type of data, okay? And this is a classification task. You have here red X's and blue X's, and you want to be able to classify a new X if it's red or blue. So the first thing we did, we took this data and we split it into two parts, R1 and R2. And notice that R1 is very smooth and nice and easy to classify. And R2 is like this crazy function that is going to be very hard to classify. So we're going to assume in our approach that one of the parts is easy to classify and the other is harder to classify. And now our active learning is going to be the question of, assuming you have new example, should you take it from R1 or should you take it from R2? If the answer is R1, that means you want easy examples, typical examples. And if the answer is R2, that means you want more uncertain examples. And how that's going to look? So do you guys can see it all right? Okay. So how does it look in the I budget? So can you see where is my, okay. So this is the data, and I have a lot of data. So this R1 is pretty easy, so the error in it is very small. R2 is a bit harder, so the error is a bit larger. And if I will focus on R1, what would happen? Then I would be almost perfect on R1 because it's very easy to learn, but I'm going to do terribly on R2 because it's very hard to learn. So actually, my error is going to decrease because the error on R2 was already pretty large, and I'm going to do much worse. On the other hand, if I focus on R2, then what would happen? That R1 wouldn't be that much affected because it's very easy. So I could learn it with many examples or with few examples. It would be easy. But now I have so much examples on R2, so I would do better. So we would actually should pick examples from R2. So that's what most people did. That's in high budget, you should take 100%. However, what would happen if you have a very low budget? Let's say you have only like 10 access or something like that. If you're going to pick them from R1 or R2 in a random way, then you're going to do terribly on R1 and terribly on R2 because you have like 5 examples. If you're going to put all the 10 examples in R2, then in R1 you're going to do terrible because you have no examples there. But also in R2 because 10 examples are not enough. So you're going to do even worse than you did before. But if you're going to focus on R1, so now you're going to do terribly on R2. That's okay. You did terribly on R2 no matter what. But in R1, you have now enough examples to start doing something that is meaningful. So actually, in this region, you should do you should sample from R1. So this gave us this qualitatively different behavior depending on how much budget you have.
What was the model that you were putting in?
That's an excellent question. I don't know if this is universal, but in the university, when someone asks you a question that you just have a slide on it, you say it's an excellent question and, and go to that slide. Okay, so the model we did here, so this is all theoretical. Basically, we just assume we have 2 learners, one of them learning R1 and the other learns R2, and they learn them independently. And we don't really care which kind of models are they, but all we care is we can measure their errors. So what we are doing is we are measuring a function that says if you add this many examples, what the error would be. If you add that many examples, how the error would be. And we assume that R1 is easier than R2. So in R1, the error might go way faster than the error would go in R2 because R1 is easier. And then giving some assumptions on how this error looks like, pretty much all you need that these errors would look like an exponential function or decrease even faster. And if you measure it on real networks, this is a function you can measure. Then exponential function is very, it makes sense. I mean, if you actually measure it, it even goes faster than exponential function in most of the models we tried. Linear networks, neural networks, SPM, whatever we fit it in, it was exponential. So the model is just a combination of these two models that all we know about them is this error. And when you do that, you actually get you actually get a threshold test that you just plug in this error function that you have, and you plug in how much harder the R2 part than R1, and you plug in all these parameters of the problem in, and then you get a number. And if this number is larger than some scalar, then that means you should sample from R1. And if it's very smaller than that scalar, that means you should sample from R2. I know this is a bit end wavy, but I'm trying to show you the idea. If you want to hear more about the theoretical, let's talk about it in specifically. But this is the kind of analysis we did. Sure. Sure.
What is the notion of good here? So if I have an infinite number of samples, then
infinite is a problem. Infinite is always a problem. Okay.
So if I have an infinite samples, then I cannot leave R1 and R2 alone. I have to do both.
Yeah, if you have infinite number of samples, you have infinite number of labeled samples.
Yes,
so if we assume that you are in the high budget almost. Yeah, it's no longer the interesting regime because the regime is when you have only few labeled examples.
Exactly. So now let me come to the what I would like to say is that for an infinite number of samples, we would like to get both of these. Now, if you have very few samples, then what does it mean to say that the hard examples should be chosen earlier or later? Because at the end of the day, you have to say what is the best thing you can do with these many samples.
Yeah, I mean, if you have infinite number of samples, then
no. So let's say you have 10 samples.
Okay.
And now you have to. I guess this slide is about choosing where these 10 samples lie.
Yeah.
So they lie in R1 or R2.
Yeah.
Even if you completely solve for the optimal place to put these 10 samples, you would still have to measure what is the regret coming from having infinite samples. You can let it measure.
Yeah.
Yes. So if we come up with an active learning solution that places the 10 samples in some place, we should compare it to. We should measure.
Yeah, we should compare it to the one that did.
It depends on how big R1 is under the Labeg measure versus R2.
Yeah, so you're absolutely right, and this is all the stuff that I like swept under the board here. But basically, when you see the parameters that I did not mention here, so alpha here is saying how harder R1 and then R2, right? How big it is. But P over here is what you're suggesting. So P is what is the probability that example would even be in R1 or in R2 in the general case. And you can see that if P is very large, let's say all the examples are in R1 or most of them, then you get that you want to sample from R1 for much longer, because R1 examples from R1 would affect your generalization error in a much better way, because most of the examples are coming from R1. So learning R1 would affect your generalization error better. So this is all in the.
The R1 model better. So I think there's a little bit of circular argument going on here. If you don't know the distribution of data, then the only understanding of the distribution that you have is what dependent on what hypothesis class you pick. If you pick a small hypothesis class, then you can get a few more samples and pick it. If you pick a complicated hypothesis class, you need a lot more samples to pick it. Now, what you are introducing here is another notion of where the samples are coming from. But
yeah,
we need to know about both of these things, how difficult the initial distribution is and what is the class of models that is fit in both of these two parts.
Yeah, I don't assume that this is not practical to do that, right? I mean, I don't know in advance how much examples I'm getting and how much and which part is harder than the other. But so in practice, I can't do this sort of analysis. But in theory, I know the problem. I know which part is easier and which part is harder. I assume that R1 is that much harder than R2, and I assume that I know the probability that examples are coming from R1 and R2. And assuming I know all that, then I can, like in Indelsight, tell you which active learning method you should have used. Yeah, so in practice, this is only theory, but now I'm going to show you like what we did actually in practice about this type of stuff. Actually, okay, in time. Okay, so so this is going to be again the theory, the practical stuff is going to come a bit later. But what I'm going to show you here, so basically the x-axis here is going to be the budget size. It's going to be how much examples I can label. And the y-axis is going to be, I'm going to plot each strategy on this graph, and the y-axis is going to be if this strategy is better than doing no active learning at all, or is it worse than doing no active learning at all. So I'm going to show how each different strategy is going to change according to the budget in this theory that I just presented. So if we take what most people do, which is sample from R2 from the other parts, so what we get that until some point in budget for the low budgets, then actually sampling from R2 is going to hurt you. But at some point, when the budget gets big enough, then sampling from the other examples is going to be actually better than random. And if we take the strategies that taking stuff from R1, we're going to get the exact opposite. So if you take examples, if you have only few examples, then our method is going to be well. But if you have many labeled examples, then our method is going to be very, very bad. So this is all theoretical, but you can actually measure it in practice. So we suggested a method that samples only the most typical examples, the method which I will present in a moment. And we took the active learning methods that are people actually using, and we just measured them in different budgets. And we can see that, let's say that the margin active learning strategy, which is a common active learning in the literature, then we can see that in low budgets it fails. It's sometimes even worse than random behavior. But when the budget gets high, it gets very, very good. But our method, which does the exact opposite, then whenever uncertainty works well, then our method fails. But in the low budgets, when nothing works well, then our methods manage to do well. And this is very similar to that.
What does no active learning mean? It just means random samples.
Yeah, it just means you have these many random samples and you train model on them. Okay, so what is this our method that I'm suggesting here? What did I do here in the purple line? So yeah, sure.
But don't most active learning methods think of task difficulty, sample difficulty differently? So if you go to your previous slide, most I guess the one this one. Most active learning methods try to sample points that are close to the boundary.
Yeah.
Define difficulty in that sense. So you can combine your idea and those ideas together in better method. So you can select samples in R1, but you also want to stay close to the boundary. So it's not necessarily as simple as easy and hard. It's easy in the sense that it's an R1, but it's hard in the sense that it's close to the boundary.
Yeah. So it really depends on your problem and on your model, right? I mean, the model, you're probably thinking about, I don't know, SVM or something like that in mind. But this is more of like intuition than anything else, because the easy could be anything. Easy or hard. The point is that I did not really define how did I split this data into. So I could split it into, let's say, by saying examples that are near the boundary and examples that are far away from the boundary. And then I could use the exact same theory. And then I would get that at the beginning you should take examples that are far away from the boundary, and at the end you should take examples that are near the boundary. So
you always want to be near the boundary.
So in SVM it's not true anymore, because even in SVM it's not true. But imagine you have, I don't know, you have like two Gaussians and you only have one example of each step. If you pick something that is close to the boundary, you might get like very weird lines. If you pick examples that are right inside the boundaries, I mean right in the middle of the Gaussians, you're going to get exactly what you want. Maybe I need to.
Yeah, but there is also not much probability of that those two samples coming from the boundary. In expectation, two samples from the boundary in the distribution model.
Yeah, it depends on your data. I agree. It's not that simple. No, there is actually a paper now in IC, not ours, but a paper in the recent ICML, which did exactly what I'm telling now. So what they did, they actually took two Gaussians and showed that if you try to learn SVM on them, so you should sample the examples. If you have only few examples, you sample them as close as you can to the center, because if you sample them from the entire Gaussian, then you're going to get examples that are they are close to the boundary, but they are very far away from each other, and they're going to do like very bad stuff when you try to train SVM on them. But this is not my work, so I'm not sure I want to like stand behind it. But yeah, the idea here is that you should do different stuff when you have a lot of data and only few points of data. That's what I'm trying to get. It's qualitatively different behavior. Can I
Yeah.
matter.
Are you imagining, or are you in practical applications? So are you like continuing to train a model that was trained? So when you add a new sample, are you continuing to train?
You say this?
Yeah.
Okay.
Are you doing incremental learning,
No,
or are you
so
training the network from scratch?
this point here, I started with, let's say, I think it's 20 examples, and then I trained 20 examples of chosen at random, 20 examples chosen by margin, and 20 examples chosen by our method, and trained by scratch. And then when I moved here, I picked 100 examples totally from scratch, and
but you could imagine like combining the insights from the curriculum stuff. Right?
So yeah, I'm doing it iteratively also works. That's not what I did here. Okay, so what is the method that speaks the most, which is the difference between uncertainty and here? So here I want to pick the most typical examples, but I want them, I'm in unsupervised regime. I don't have labels of the data. So what we do, we took the data and we just ran some unsupervised method on it. Let's say SimSimilar, Dino, Scan, pick your favorite. And then we got representation space for that data. And what we did, we simply picked examples that are most dense in that representation space. So the examples that the k nearest neighbor of the examples was the least. And when you do that, you get this type of stuff. So apparently this is CFAR. CFAR is a very bad data set. Apparently there are like 500 cars that look exactly like that in CFAR. This is without segmentation. This is just real how CFAR looks like. And if you take the examples that are most dense, then this perform a very nice little cluster. And these are all the most dense examples. So this is not what we want, because this is one image. So what we did instead of that was taking the most dense example, but trying to take it from different parts of the data set. So we took this representation space and we simply clustered it into many clusters. So let's say we wanted to sample 30 examples. We just clustered it into 30 clusters. And then we picked the most dense example in each cluster. And when we did that, we got these examples. So here, the car is still here, that's one car that appears like 500 times. But we started to get different examples as well. And we didn't try to, so every column here is a different class, but we didn't, it's unlabeled. We didn't know we're gonna get different classes. So it's by chance, it's almost class balance, but it doesn't have to be. And this is the method. I mean, this is how we pick the most typical examples, but make sure that they are spread out during the entire task. And when we do that, we can start. Now we can actually see how it looks like in low budgets. So here I train on CFAR. On the x-axis, I just train the number of examples, and in the y-axis, I have the accuracy. And the black line is training random examples. The blue line is training using our method. And all the rest of the lines is just taking different type of active learning strategies. And you can see that as the theory predicts, all the active learning strategies are all based on uncertainty sampling. So in this low budget, they should fail, and they do fail. And our method is actually suppress them by a very large margin. And I'll get to the bottom in a second, but in the top you can see it's on different data sets. So it's also happened in CIFAR 10, on CIFAR in ImageNet and stuff like that. And this has the most impact that this type of results have is in semi-supervised frameworks. So in semi-supervised frameworks, you have a very low amount of labeled data and very large amount of unlabeled data. So you're in the low budget regime almost by definition. And the goal is to do the best you can with as little labeled examples as you can. So what we did here, we just took the best, the state-of-the-art semi-supervised method for these data sets, and for example, in this experiment over here, we just took 10 examples from CIFAR, and we either took them by random or choosing them by our method, and then ran a state-of-the-art semi-supervised method. And we can see that the improvement is almost 40% more. So doing training of this 10% so far been like 54% accuracy or something like that. And using our replacing the examples with the most typical ones can increase it to over 93% accuracy. So this is a very big type of improvements. And okay, but this took me a bit longer than I expected, so I'm not sure I'm going to. I had another work that I wanted to show, but I'm not sure that I managed to do that. Okay, I'll start and let's see where we're going. Well, when should I finish? 4-ish. Okay, so I'll do it like quickly. Okay, so far we've seen that it actually matters how you present the data. In the labeled cast, we saw curriculum learning, and we saw that easy examples are better at the beginning and other examples are better at the end. And in the unlabeled cast, we saw active learning. So when you have a very few labeled examples, you should do like easy examples, and then we have very high number of examples, you should do other examples. But all of this works focused on how we should teach the network. What we did afterwards, so this is not chronological order. So what we also did is to see how the networks themselves train. So not what we should show them, but if we actually analyze what they did learn in each stage of the learning, what would be more important for them, what would be less important for them, and stuff like that. So I'm going to skip the motivation here from humans, and I'm going to go straight to what exactly we did. But basically, what we want to do is to know how similar different networks learn. We know that humans learn in a very similar way. If I have 10 children and teach them the same tasks, they most likely will do similar kind of mistakes. And I wonder if networks would also be like that. So the first thing we're going to do here is going to take a network, a specific architecture, and just duplicate it and train them twice on the same data. And when I do that, I'm going to reach different local minimas, because this is stochastic gradient descent. But I'm going to assume that people usually know that that's what happens, but they assume that this is kind of okay, right? Because both of these networks tend to have the same accuracy, so they don't really care where the local minima is. They can't even compare these local minima, but people usually ignore that. They say, yeah, that's pretty much the same network. So what we're going to say that it's not only that they are the similar network, they'll only learn pretty much similar functions. So in all, they're going to do exactly the same on many different kinds of examples. And not only that, what's happened here? Okay. So not only that, even if I take different networks, like one of them going to be in very different architecture, then I'm going to get that they're also learning pretty much the same function. I'm going to define what this pretty much same function means, but they are much more similar than one would expect. But I need to do that in 5 minutes. So let me explain how exactly I did that. So the first thing we want to do is to measure new things. So instead of measuring accuracy, I'm going to measure accuracy of, instead of measuring the accuracy of networks, I'm going to measure the accuracy of specific images. So let's say I have 3 models trying to classify these trees or hamsters datasets. And I have model A, model B, and model C. And let's say model A, all these 3 models managed to do 2 images correctly, and the other one didn't. So if I measure accuracy, I would say that all the models have 2/3 accuracy, right? But what I'm going to do here, I'm going to measure the agreement of these networks over each example. So on the example on the right, we can see that all the networks manage to classify it correctly. So this example is going to have one agreement. On the example on the left, only the two first models managed to classify correctly. So this has 2/3 agreement, and the middle example have 1/3 agreement. So even though all the models have the same accuracy, the agreements could be very different between different examples. And now that I have this agreement for every image, I can look how this agreement distributed across different across all the data sets. And what we find, so we have two different options here, right? If all the networks are very, very similar to each other, then the distribution is going to be like this very bimodal. For every example, either all the networks agree on that or all of them disagree. And if all the networks are not the same, then I would expect to have a distribution that looks something like that. Maybe it's going to be like Gaussian around some number. And what we get in practice is something like this. So it's not perfectly bimodal, but it's almost bimodal. So for most of the examples, most of the networks really agree. And so this means that at least at the end, the networks learn pretty much similar function because they managed to do pretty much the same thing over all the examples. And this also happened during the entire learning phase. So I can do this type of analysis at every epoch and can see that even after a first epoch or second or 2 or 10 or something like that, you can see that this is always bimodal. So the network actually learned a specific, in a very specific order. First, they learn all the examples that are here, and then here, and then here, and then here, and so on and so forth. And this has actually let me measure a specific order for networks. So every network has a very specific order. And once I have this order, I can actually try and see if this order is similar for different type of architectures and stuff like that. So let me do many skips and show you this type of results. So here I learned ImageNet. And what I plot is just a plot for every example, the order in which it was learned in one architecture and the order in which it was learned in a different architecture. So we can see that this order, the correlation is like 0. So here, if you look here, the correlation is like 0.97 or something. So the examples are very much learned by different models in a very similar way. And if I look on the left graph, so here ResNet and AlexNet are very differently sized networks. I think AlexNet is much weaker than ResNet. So AlexNet reached like 60% and ResNet like 80%. And even though that happens, the correlation between the order is very, very big. And I really want to stop here, so I won't go any farther than that. But to give my final point is that if we're actually going to look on which examples were learned by these AlexNet and ResNet, remember, AlexNet is much weaker, then what we're going to find that ResNet actually learns all the examples that AlexNet can learn. And then when it reaches the point when it learned all the examples that AlexNet learned, it just keep on and learning new stuff. So it learned the same order until it's managed to do exactly what AlexNet did, and then just learning more and more complicated stuff at the end. But let's finish here because I'm already over my time, probably. No, I'm not, but let's finish here. And if you have more questions, then I'm here all day. You can come talk to me or whatever you want. And thank you very much. Question?
I think you have quite a few work on a paper that you didn't talk about, which follow up this work, right?
Yeah, I have quite a few other works, but this felt to me quite dense already.
Yeah, I recommend the principal component bias. That was really good. that follow up this paper, right?
Yeah, so the principal component paper just basically tried to explain the order in which the networks learn. So here I just showed you that the networks learn in a very specific order, but what is this order? Then we have another paper that starts to explain this order. Pretty much we claim that at least in the case of images, this order is highly dependent on the principal components of the data. So if there are examples that could be learned using only few principal components, then these examples are most likely going to be at the beginning of this order. And if they could be learned only using a lot of principal components, then most likely they're going to be at the end of this order. But yeah, didn't have time to include that.
Principal component of only X, or like, are you somehow combining it together with the task? Like, is it a task dependent already, or is it
No, it's independent of the labels. We actually
weird though, right? Because you would imagine that the same example
So
can be
it-
hard for some tasks and easy for others.
so it actually, yeah, you're right, it does, and we actually showed that it does. But all of this theory is like is for linear networks when it doesn't. In neural networks, you're completely right. You can actually build a task like that. But yeah, that's only preliminary results. So
That sounds very cool.
sure. Anyone? Any other things you want to ask?
I have a question on this last bit.
Yeah, sure. I didn't explain it quite well, but sure.
Well, I think I got the gist, and I guess I'm pretty curious. You seem to have framed it as a property of models.
Yeah.
I'm wondering if it's a property, there's a way to teach properties of a property of data. Because at least in
Okay.
many data sets, samples that make it in are samples that humans have had it in.
So we tried the same thing with all these architectures and all these data sets, and we found the same things in all of them. So that's why I'm thinking it's more of a data set, model related thing, but we did focus mainly on images. We did have one work, this is a different paper which I did not cover here, which seemed a very, very similar results with language models. So we also suspect that it's going on there. So because we never actually managed to find any evidence that it's data related and not the other way around, that's what we assume at this point. But you never know for sure. Sure.
Okay, good. That's thanks, Dan. Great talk.